Welcome back to the final installment on the intake development for the BMW G80 M3 and M4. In this video, we're going to look at the carbon system, which is the final production system. We'll also look at some performance data and something brand new in terms of technology, which we've never used before on an intake, and I'll show you that in some detail. Without further ado, I would like to introduce you to the brand new Eventuri BMW G80 M3 M4 intake system. In front of me, I've got the main components of the new intake, all in carbon fibre, as you can see, apart from the inlets. Everything is made from pre-preg carbon fibre, so there is no fiberglass used. It's carbon fibre through and through. I've got the right-hand side of the system as you look at the engine over here, and the left-hand side over here. And you've got a fully sealed system, which is why there's so many components. And we'll show you what it looks like in the car. But first of all, let me just briefly look at the individual components first. We have done a detailed comparison with each part as compared to stock in the previous video. So if you haven't seen that, please do go back and have a look at that video first so that you can understand the context of what I'm about to show you. So starting from the right side of the engine bay, we've got our filter housing, the Venturi style filter housing, the main tube which connects the tube to the turbo inlet, and then the duct which seals against the mouth of the housing. So looking at the housing first, the side profile, as you can see, it has a swooping kind of shape, and that's to avoid some ancillaries in the engine bay, which allows us to make the overall shape quite smooth internally. We've got a large filter opening, and as explained in the previous video, this is a bespoke size which we've never used before, and we've developed this filter size specifically for this car to make use of all the volume that is available in the engine bay. So this sits against the duct like that. So once it's installed, this filter housing breathes from the stock duct opening down there, and also from a separate opening which extends into the wheel arch area, which we've shown you also in the previous video. And you can see inside that duct the carbon weave, which shows you that it's not fiberglass at all, it's fully pre-preg. So this duct sits against the wheel arch area, so that rubber edge sits against the wheel arch area and just seals against it, breathes from the stock duct, and breathes from the opening between the wheel arch and the chassis. The tube itself, again, pre-preg carbon fibre. We've made it as big as possible. So you've got a large 4-inch opening on this side where the filter sits, which then continues that size as much as we can, and then tapers down right at the end to the turbo inlet side, which is over here. We've got integrated brackets made in carbon again, which just positions that where it needs to be. And then we've got a nice transition, a nice curve down to the turbo inlet. Finally, we have the turbo inlet itself, and this fits in the car like that in relation to the carbon tube, and between these two there is a custom-made flexible rubber section to allow some movement. So the turbo inlet itself is made from a thermoplastic to withstand the heat. It also has a CNC machined ring for strength, which is where the hose clamp is able to apply some pressure. And as you can see on the inside of that turbo inlet, there are some dimples. And that's what I was referring to in the introduction to the video when I mentioned a new technology. We will look at that in some detail later on. So in front of me now I have the other side, and as you can see there is one less component, and this is because the left side is actually closer between the turbo and the air inlet as compared to the right side. We don't have to negotiate all the way across the engine bay to reach the turbo. So I've got the filter housing, again using the same bespoke filter which is custom made for this application. We've got the duct itself which the filter housing mates to and seals against, and on this side it sits like this. So you've got the duct which sits right up against the slam panel and breathes from behind the radiator around the headlamp area through this opening. And we've made that opening as big as possible, which is actually a lot bigger than the stock duct, which you'll see on the stock airbox, as again you'll find on the previous video. And the duct itself extends across the chassis area, and you've got the input to the filter. This housing then directly fixes onto the turbo inlet, so there's no tube between them as there was on the other side. Again, the turbo inlet is made from a thermoplastic. Again, you can see the dimpled interior. This fixes pretty much in this orientation, and you've got a direct path between the filter and the turbo on this side. So it's very straight, very direct. So I've got in front of me the turbo inlets for the G80. Now we did do this comparison in the previous video, but I thought we'd do it again with the final production version. So looking at the right side turbo first, the internal diameter of the stock inlet is 65 millimeters, and the internal diameter of the Eventuri version is 83 millimeters. That gives you an increase in cross-sectional area of 63%. So the Eventuri version is 63% bigger at the interface with the intake as compared to the stock inlet. They both have a very similar curve down to the turbo, and then again at the turbo side they do match, which is important because you don't want to step just before the turbo. Let's look at the left side inlets. Now straight away you can see there's a huge difference in the internal diameter. The stock inlet diameter is 54 millimeters and the Eventuri is 87 millimeters on the inside. That, in terms of cross-sectional area, is a huge 160% increase with the Eventuri inlet. Obviously you can see that visually as well, which is a massive difference. Again, it tapers down to the same diameter at the turbo. Now, a question which has been raised previously when we've increased turbo inlet diameters on the inlet side is, well, if they're going to both taper down to the same diameter, does that make a difference in terms of what we do on the other side? And the answer is yes, because the overall drag of the inlet is reduced when we increase the total volume. Because the airflow has to travel through that section, if that section is small all the way across, the friction and the drag is bigger as compared to when we increase it as much as possible. Even though it tapers down to the end, that diameter is in terms of the path is smaller as compared to this one, whereas you've got an increased volume on the Eventuri. So it does make a difference, which we saw on our Audi C8 RS6 inlets. So increasing the volume of the turbo inlet is just one way in which we can reduce drag. Something which I've been looking into for a number of years and I've done a lot of research around is the actual shape of the airflow as it flows through a tube. And something which I've known for a while is how a golf ball works in terms of the dimples and what it does to the airflow as it travels through the air. And it's a well-known fact that a dimpled golf ball travels further through the air as compared to a smooth golf ball. Now, the mechanics of that are slightly different when it comes to flow through a tube, but the principles do carry over. So something I've been researching into, I've read a lot of scientific papers around using dimples and the effect they have on airflow in terms of reducing drag and increasing flow rates. And I am very excited to show you and share with you now what we've done in terms of implementing that technology into a tube, and specifically for a turbocharged car. So I'm now going to show you what we've done with this dimpled inlet and the reasonings behind it. I've shown you an introduction to the intake and you've seen the turbo inlets. I briefly showed you the internal surface of those inlets, which have dimples in them. So I now want to try to explain to you why we did that and the physics and mechanics behind that theory. Before I do that, just a couple of background notes. So when we manufacture intakes, the normal process uses either carbon fiber or some sort of cast or injection molded process. For us, it's normally carbon fiber, and in that process, there's not a lot we can do to modify the internal surface rather than try and keep it as smooth as possible. However, with this intake in particular, we've used some very cutting-edge techniques to make those turbo inlets, which gives us a lot of freedom in how we design them. And with that in mind, it allowed me to then experiment with changing the internal surface to increase the flow efficiency through those inlets. So when we look at flow through a normal tube, there's two things we need to consider to try and increase the efficiency of the flow through that tube. The first thing is the pressure drop. So if I call that delta P, as in pressure drop, difference in pressure. And the other thing is the flow rate, which we'll just say is R with the dot on the top, flow rate. What we're trying to do is reduce the pressure drop while increasing the flow rate. There's not much we can do about that in a smooth tube apart from make sure that the bends aren't too tight and it's as organic as possible in its shape. However, with the inlets, what we can do is modify the surface to increase the volumetric efficiency of the airflow. How do we do that? So I'm sure a lot of you have seen golf balls, and golf balls have dimples on them to make them fly further through the air in comparison to a ball without dimples. The mechanics of that and the flow through a tube are very, very different. However, it does lend itself in some ways to the same sort of theory. So by introducing dimples to the internal surface of a tube, what you're actually doing is you're almost introducing a bit of surface roughness, but a controlled surface roughness. Before we look at that, let's look at what happens when you put flow through a normal smooth tube. So if I just draw the upper and lower boundaries of a tube, any tube, you've got airflow going through the middle of that tube to the turbo or to the engine. And what we're trying to do here is increase the flow rate while reducing the pressure losses. And the pressure losses happen at the boundary of that wall and the airflow. Airflow, when it goes through any tube, contacts with the boundary wall. And what happens at the boundary wall is the velocity of the airflow is greatly reduced because of friction. So if I show you what happens in terms of velocity, the velocity at the wall is very low. So if the length of my arrow denotes the actual velocity itself. So you've got low velocity at the wall, and as you come away from the wall, that velocity increases when you get to the center of the tube. It's at its maximum. Then as you get closer again to the wall, it reduces, and it continues to reduce until we're at the wall where it's very, very low. If I draw the velocity profile now, just complete this is what you get. So that curve is your typical velocity profile of the airflow going through a normal tube. What we want to do with Dimples, by introducing Dimples, is increase the velocity of that airflow near the wall. And how does that happen? I'm going to just rub this out. So let's draw the wall again, but I'm going to now introduce a dimple. The trick here, and the reason why it's taken us so long to develop this intake, is this technology or this theory hasn't really been experimented and used much in reality. There have been simulations in CFD, there have been papers written about it, but no one has really gone down the length of doing what we've essentially done, is actually implement this theory. So the trick is to change and adjust the size of the dimple and the shape of the dimple to cause the airflow to detach from the surface and to create a controlled vortex or a recirculation zone. So what we're trying to do, I'll use my red pen, is create a zone of recirculation within that dimple, so that the airflow, when it goes past the dimple, is actually going over that recirculation zone, and the velocity will be much higher as compared to no dimple, where the velocity, where the airflow is almost touching the boundary wall, and you get that friction. So what that's doing is almost like a ball bearing, is it's allowing the airflow to escape past the wall, and you've got a cushioned effect layer. So you've got a layer above and below across the surfaces of that tube. So if I now make more dimples and complete that, so we've got recirculation zones in each of these areas. And so what happens is that the flow rate across that surface now is a lot faster. So what we're trying to achieve, just remove this one, is a velocity profile which is more evenly spread across the surface of the tube. So now we've got something like this. So the distribution of the velocity is much more even as compared to what it was where there were no dimples and the surface of that flow was touching the surface of the boundary layer. Now, there are lots of complications here which I won't go into, but in effect, if we make the dimples too big, you don't get that recirculation zone. The flow actually goes in and comes out, and you increase the pressure. If you make them too small, then you can't make them for a start, and you don't have the beneficial effect of the vortex, creating a cushioned layer between the main body of the airflow and the walls of the tube. So that's a brief rundown of what happens with a dimpled surface through the turbo inlets. And we've implemented that in our turbo inlets on the G80, and I've shown you those. Now what we'll do is we'll have a look at some of the CFD simulations we've run using our designs of those turbo inlets. With the theory explained in terms of how the dimples work, let's now look at how we've implemented that onto the inlets themselves. I've got in front of me the original design of the inlet. So we explained previously how we've maximized the volume on the intake side, which is there, and the airflow then moves through that inlet to the turbo side on this end. So there's nothing wrong with this design. Does the job very well, but I just felt like the G80 was the platform to push the boundaries and implement something I've wanted to do for a long time, I've read about for a long time, I've researched, and it just felt like the right time to introduce it. So let's now have a look at what we've done with the dimples and how the inlet looks. There we have the inlet now with the dimples applied on the inside. They move all the way through to the turbo side. Here's a cross section through the inlet, and you can see how those dimples are applied all the way through the internal surface. The dimple design on the inlets was optimized using CFD. So I've got in front of me some of the initial CFD analysis we did with that design on the left hand side turbo tube for the G80. On the left we've got the inlet with no dimples, so just a smooth surface, and on the right, as you can see, there are multiple dimples across that surface, and this is a cross section across the inlet. The colors you can see denote velocity in meters per second. Blue is low velocity and red is high velocity. On the left hand side you can see areas of high velocity at the exit, and they reach a peak of 170 meters per second. Just to point out that we added boundary conditions on this analysis so that they replicate what's happening in the real situation. So on the exit of that pipe or the tube where it attached to the turbo, there is a boundary condition of an output flow. So flow is being pulled through that tube. We're not actually pushing air through from the opening, because that wouldn't be correct. So we're pulling air through as it would be in the real case. So on the left side we've got a maximum flow of 170 meters per second with no dimples, and on the right you can see a maximum flow velocity of 188 meters per second with the dimples. So straight away we can see that the velocity is higher using dimples, and you can see a region just above those dimples of lower speed, which is where that cushion is being formed across those dimples. Whereas on the tube with no dimples, you can see there is no layer across that boundary surface, which is where you get those shear stresses and the friction and pulling the airflow in so that you don't get as much of a high speed. Okay, so now I've got the diagrams up showing the ISO lines, so you can see the direction of the flow. It's not that clear, but on the left hand side the ISO lines are not as smooth as they are on the right hand side with the dimples. And the reason for that is because, again, as I showed you previously, the velocity profile when you're using a smooth surface, you have very low velocity at the boundaries and increased velocity in the center, so your total velocity profile isn't uniform across that tube, whereas with the dimples it's much more uniform above the dimpled surface, above that cushion layer. So you get a better, more even flow rate, more even velocity profile through the middle of that tube. So I just wanted to show you a close-up of what happens within the dimple itself. So in the CFD simulation we've actually managed to show the circulation effect, which I explained downstairs. So as you can see on the screen, we've got the dimples, we've got the velocity profile, and you can see here within the dimples there's a recirculation going on. So there's a controlled turbulence within each of those dimples. Is a cut plot, so you're not actually seeing the entirety of what's going on, but where the surface is being cut, you can see within each of those dimples that blue circulation of the flow, and that creates that cushion effect. So you can see just across that boundary there's like a green zone, which is a low velocity but a cushioned surface. So you've got airflow contacting a low cushioned speed of airflow, which pushes and allows the majority of the airflow through the middle to slip through. So I hope that sort of shows you and explains from a CFD point of view what's going on, and it explains the theory which I explained previously. To summarize, we know how well the dimples work in theory, in the CFD simulations, and we are very excited to bring this to the market as something quite new. I know there have been some attempts at something similar, but not quite to this level of detail and analysis. And as an engineer, this really does excite me to be able to research, read about, and implement something in the real world, something which I've read about only in theory and in papers, and then to do our own analysis, to do our own research, to simulate it in CFD, and then to actually bring it to the real world and to an actual performing intake, which will be on customers' cars, is just, it's just amazing. I can't explain how much that makes me happy as an engineer. So I do look forward to seeing these on cars and getting feedback in terms of how the intake as entirety feels. I can see this being used in other intakes where possible, where we're using such advanced manufacturing techniques, and we are looking forward to seeing what the future holds for this technology. So we've seen the design in total. Now let's look at some data logging, which is what I'm sure most of you have been waiting for. So the first thing we'll look at are temperature logs, so the inlet air temperatures. The purpose of doing this was to see what the intake itself was doing to the air temperatures, and it's important because while we're trying to maximize airflow, so to de-restrict the system, what we didn't want to do was compromise on temperature. And we could very easily de-restrict the airflow by using an open cone system, but then obviously you'd be pulling in hot air from the engine bay. So what we've done is we've maximized airflow by increasing volumes but keeping it sealed, so it should in theory perform in terms of temperature in a similar fashion to the stock airbox, which is obviously sealed. So we placed thermocouples on both of the turbo inlets, so just before the turbos, one on the left side turbo and one on the right side turbo as you look at the engine bay. And we took the car out on a closed circuit on the same day, so about 10 degrees Celsius ambient temperature, and we drove the car in 6th gear, allowed the car to get to 30 miles per hour, and then we accelerated in 6th gear only to 90 miles per hour. Once we hit 90 miles per hour, we then decelerated by braking down to 30 miles per hour again, then we accelerate again to 90, and we've repeated that 3 times. Before the tests were started, we allowed the engine bay to fully heat soak and saturate with heat. So the intake was heat soaked, the engine bay was heat soaked, so both systems started at the same point. So let's look at the data. In front of me I've got 2 graphs, one on the left, one on the right. The left graph is for the stock airbox and the one on the right is with the Eventuri. The blue lines at the bottom denote the ambient temperature, so you can see it's around 10.5 degrees to 11 degrees, which is quite consistent throughout the session. And above you've got the green lines, which are the temperatures for the right hand side intake, and the orange lines, which are the temperatures for the left hand side intake. So again, the temperatures are just before the turbo. So let's look at the graphs and see what they mean. Now, as I mentioned, we accelerated to 90 and decelerated to 30 3 times. So you've got here that reduction in temperature is when the car is accelerating. So you've got airflow rushing through the intake, going past that thermocouple, and as it's doing that, the temperatures are reducing, obviously. So at the bottom of those graphs, so you've got one here, another section here which are decelerating, and another section there which are decelerating. That's at the end of the run, when we hit 90 miles per hour. As soon as you let off the throttle, that temperature peaks. It rapidly climbs, as you can see there. And the reason for that is because the cold air is stopped. It's now no longer rushing through the intake, so all the heat from the actual intake itself around the outside of the material suddenly penetrates and saturates the interior of the intakes. And that's what happens with each of those peaks. So we accelerate, temperatures drop, come off the throttle, temperatures rapidly climb, and this section here where the temperature is fluctuating is when the car is decelerating. So we're not applying any throttle, we're just applying the brakes, and you've got the car decelerating. We then accelerate it again, so you've got another section of temperatures dropping, and then the process repeats. So on the stock airbox, at the end of every acceleration run, on the left side we've got around 29.7, so just under 30 degrees Celsius on the left side intake, and 31 degrees on the right side intake. And that dropped a bit on the second run to 26 degrees and just under 28 degrees, and then again dropped again a bit more to 23 degrees, and then 24 degrees for the right side intake. The reason for it dropping is because every time you accelerate, more cold air is going through the system and it's cooling down the actual material of the intake. So you're progressively getting cooler and cooler. Right, that's the stock. And the Eventuri intake on the right side is quite different in its characteristic. So the obvious thing here is when you're looking at the left-hand side intake, it's dropping lower than the stock. So we've got 23 degrees as opposed to 29 or just under 30 degrees. And interestingly, when we come off the throttle, that peak temperature as it suddenly rapidly climbs on the stock intake is not happening on the Eventuri intake. So whereas on the stock intake, that left-hand side intake went up to 91 degrees Celsius on the first run, and then it went up to 83 degrees Celsius on the second run when we let off the throttle, which then equalized to between 60 to just under 70 degrees Celsius on the deceleration. So it shows you with the Eventuri we're equalizing, so it actually peaked at 38 degrees and we're equalizing much lower as compared to the stock intake when you're decelerating. So basically the Eventuri is dropping lower with the IAT on acceleration, and it's also maintaining that temperature when you come off the throttle and you decelerate. On the right hand side intake, we're pretty much even on the temperature. So we've got 31.4 on the first run, and we've got 31.8 on the Eventuri. So we're around the same, and that again drops on each successive run. What I'm going to do is superimpose this data on top of each other to show you more plainly what's going on. So I've got a graph now in front of me which shows you the left-hand side intake for both the stock and the Eventuri superimposed on top of each other, because obviously that's the biggest difference. So it clearly shows you the green line here is Eventuri, the orange line is the stock intake, and you've got at the end of the acceleration run 23.6 degrees on the first run for the Eventuri and 29.7 degrees Celsius for the stock airbox. When you decelerate, when you hit the brakes, that rapidly climbs to 90 degrees and equalizes to just around 70 degrees on the stock, and on the Eventuri it's less than half, so you're at 38 degrees equalizing to 43 degrees. Why is that? Partly that's to do with the materials we're using and also the path that we're taking. So on the left side of the intake, the stock airbox has to follow through a tube which bends around into the top of the airbox. Then that airflow goes down through the filter, or it's being pulled through that filter, down again 90 degrees through the duct. So it's quite a convoluted route from the air intake of the duct all the way through to the turbo. Whereas on the Eventuri it's very direct. So it goes straight through the duct, straight into the filter, which is that housing which we showed you with a conical filter, and straight into the turbo inlet. The other reason is the material. So on the stock system, you've got the turbo inlet, which is made from cast aluminium. And obviously aluminium is a very good conductor of heat, and that tube is very close to the exhaust manifold and the cat. So the amount of heat which is hitting that is constant and it's very high. So as soon as you come off the throttle, that residual heat is penetrating straight into the interior of that inlet, and that's why you get the temperature spikes. We're using carbon fiber and thermoplastics on the intake and the inlet, so we don't have as much conduction of heat through the thickness of the material. So when you decelerate, it does climb, but not as rapidly. So that's a good indicator of what's going on with the temperatures, and it shows you that even though we have de-restricted the intake for airflow, we're still maintaining and actually improving on the stock airbox with the temperatures. That's the temperatures done. Now let's look at the dyno graphs. For the data analysis in terms of performance gains, we sent one of our early G80 intakes off to one of our dealers in Belgium called BR Performance, who tune cars, and also they have their own dyno cell and their own G80. So the car they tested it on was fully stock, no tune, no other modifications, purely just the intake. The temperature of the dyno cell with the stock intake was 11.8 degrees, and the temperature of the dyno cell with the Eventuri was actually higher at 15.9 degrees. So we were at a bit of a disadvantage from the get-go. However, we still managed to show some gains. Now, it is worth pointing out that the stock airbox is actually pretty good for a stock system. The only obvious restrictions were the turbo inlets, as we showed you previously. So looking at the graph, we can see some gains, and the good thing is there are gains across the entire RPM range. So looking at the torque curve, we've got gains pretty much all the way across. So looking at where it counts, so for 2,500 RPM, all the way across, you've got a decent gain in torque, and again, top end, and obviously horsepower, you've got gains starting from around 3,500 RPM, which continues all the way across, and you've got more gains at the top end RPM, which makes sense because if we're showing gains early on, as the airflow increases through the system, you'll see more at the top end. So at the top end, in terms of horsepower, we've got just over 13 horsepower. Now, the good thing is you're showing gains not just at peak, but across the entire RPM. So that means that the car will feel more aggressive to drive. And the one thing that we had repeatedly in terms of feedback from everyone who's tested the intakes was that the throttle response was much sharper. So one of our dealers in Korea who regularly tracks his car, he did a full track day with the stock airbox. He then did the same thing again with the Eventuri, and his first immediate feedback was that the car felt much more lively and much more responsive as he came out the corners and he accelerated. So that shows you that the car is able to spool up and you're getting that initial inertia faster with the Eventuri intake. And obviously you can see that on the dyno graphs with the gains across the RPM range. We've got good gains in terms of a stock car. That is good gains considering that the stock airbox is good already. We expect these to be amplified when the cars are tuned. So the more power people are going to extract from these cars, the more we expect a delta to be between the Eventuri and the stock airbox. I have now fitted the intake to the car. As compared to most of our other intakes, this is a bit more involved because we've gone all the way from the turbos. So there's more components. The turbo inlets themselves are a bit more tricky because of the packaging. However, it's all installed now. Let's have a look at what it looks like in the car. Starting from the front of the car, so the right-hand side intake. Obviously, as we showed you the housing, there's a curve to the housing, so you can see that swoop of that housing going up and then down again. That was to avoid some of the hoses underneath, but it's quite a prominent feature because it sticks up above the engine bay. So if you're looking at it from front of the car, you can see this bulge of carbon coming out and then going back down. So it's a nice aesthetic touch, I think. We've made use of all the space, as you can see, and it's very close to the strut brace. This is an aftermarket strut brace, but it's still quite close to that strut brace, as well as the duct being very close to that chassis area, the slam panel area. The space above the intake between that and the underside of the hood has been utilized with that sweeping up and down of the housing. And then moving back through to the tube, we've made that tube as large as possible, as we showed you, so there are some reliefs underneath the tube to allow clearance for the strut brace. You can't see the depth of the tube, obviously, because now it's covered, but the tube does go down further in terms of its diameter than the stock tube, following that round down to the turbo, which obviously you can't really see because it's hidden. Then moving on to the left-hand side of this engine, we've got that much more direct passage of airflow coming in now. So as opposed to the stock airbox, which sits in this space where the tube goes around and then down into the turbo, we've got our direct housing straight into the duct, which feeds straight from the front here. And you can actually see the carbon duct in this area where it pulls air in from the front. And this is the area where the stock duct also pulls air in from. It's just behind the headlamp, and it's more or less ambient air temperature. So you can see the carbon of the duct there. You can even see some carbon around the back of the headlight, because we've used, again, all the volume available. That duct then feeds the housing, and again, the housing pushes air through the filter and into that turbo inlet, which is all the way back down there. So the overall package, we've used all the volume available, we've made the airflow as direct as possible, as smooth as possible, and obviously being in carbon fibre, you've got the aesthetics of that carbon fibre look. And then all in all, as we've always used in our design philosophy, form always follows function. We never make an intake purely just to look nice. It is made to perform, and as a result of that, it has to flow well, which then lends itself to that form factor of the smooth organic curves, which is very evident throughout the design language of the entire intake. That concludes our development series for the G80 M3 M4 intake series, and we really do hope you've enjoyed our development process. We have put everything into this intake. We've left no stone unturned, and we have really tried to push the boundaries wherever we possibly could, because this particular platform is what we're known for, and we had to set a benchmark in the industry again for this intake, and I firmly believe that we have. We look forward to seeing this intake in your cars. We look forward to hearing from you. Your feedback is always valuable for us, and I hope to see you again on the next video.
Thank you so much for watching, guys. If you liked the video, please remember to smash that like button, and if you haven't already, please subscribe to our channel. If you want to join the conversation, please drop a comment below and we'll try our best to respond to you. If you want to watch more of this project, you can do so over here. If you want to watch what YouTube thinks you might like from our other content, you can do so over here.